now. All right. Good morning. We're chatting about test 2, which is on Monday, which totally crept up on me. And taking requests, we can move it, but we kind of have to all be on board. Or we can just go full steam ahead and go for it. Anyways. Well, that's the thing. If we keep it on Monday, we wouldn't have all of exponents and logs because something tells me we're not going to get through 4.6. And I actually do want to do 4.7. It's not on the course outline, but I do want to do it because it's on semi-log scales and log-log scales. And so something that you actually use. So I guess if we move it, it would be on more material. But if we keep it on Monday, I'm willing to call it at 4.5. So up to and including 4.5. Decisions.
It's 4.5.
Supposed to be today, but it's looking unlikely. Well, it's feeling unlikely. I need to change my attitude. We can do it. We're going to do it today. We're going to do it today. Okay. Let's do a little bit of review. And I found this kind of recap here. Oh boy. I want, of course, I made little notes. Okay. We ended on change of base formulas, but you also have the formula sheet now finally. So you have these log laws, and maybe that's what I'll bring in. How's that for review? Just your formula sheet. All right. So let's see here. For review, we started logarithms or logs, and we established some rules about logs. Now, this is kind of a little bit ignorable. It's a little bit excessive. Formula sheet. Two for the price of one. Okay. X and Y have to be positive real numbers. R has to be any number. A and B have to be positive numbers. So that's all it's saying, positive real numbers. And A and B can't be equal to 1. Now, B is usually the base. And so you can't have a base of 1 is what that's saying. We talked about the common log, which we don't even write the base for. It's base 10. We just write log. We talked about the natural log, log base E, which we write ln to simplify it a little bit. And so we said, this is the common log. And that's the name. I'm not just saying it's common. And this is the natural log. We established that b to the power of log base b, so notice that they have the same base of x, is equal to x, right? And so that's how we're going to eliminate a log, right, is by raising it to the power or raising it with the same base. Okay? And then that eliminates whatever the log is. The next rule that we used was if you have log base b of b to the power of r, in fact, anything to the power of r, let's skip down to 4. These are just special little itty bitty cases. But if you have log base b of x to the power of r, you can rewrite that by bringing this r down front, right, is how I kind of visualize it. And then all of a sudden, you have r available to you and you're able to solve for it because log base b of x is just a number, right? And so today, we're going to look at these next few logs, properties of logs. Multiplying inside turns into addition. Division inside the log turns into subtraction of the logs, is the Coles notes. So we'll look at that today. And we looked at this last day. This is the change of base formula. If you have to change from some log base a, usually we're going in this direction, log base a to log base b, right? Then what we can do is we can take log base a of x over the log base a. So this is the same base, but of b, which is your new base that you want. And then this rule, this change of base formula says that that's the same as log base b of x. And we saw that in an example, right? We said, oh, that's weird that these two equal the same thing. And then we introduced the change of base formula, and it turns out that they are, in fact, the same. The change of base formula is more if you have not a fancy calculator. We have a fancy calculator that you can tell it what base you want. But if you're stuck with only log base 10 and log base e buttons on your calculator, then you can still use that to calculate any base. Okay, now let's pick up some examples. End of the review. So we were just doing examples. Did we solve that already? I think so. Let me check. We did. Oh, and that's when we introduced the change of base formula. So we saw that the natural log of 2 over the natural log of 1.3 is the same as log base 1.3 of 2, right? We get the same answer. That's from last day. So we're ready for the next example, if it'll let me. What if we have to solve 6 times e to the power of 3x plus 1 is equal to 9? Now, one of the key things here is, okay, I know how to bring something in the power down, right? I want to solve for x, which is now in the power, so it's hard to get to, right? But then we think, I know how to get to that. I can use a log. I can take the log of both sides, and that'll bring this all downstairs by the log properties, right? By this property. Yeah. But in order to do that, I have to move this 6 over to the other side, right? Because I need to get just the exponent on its own. Okay. So to solve something like this, step 1 is isolate the exponent. I can do that in this case by taking 6e to the power of 3x plus 1 is equal to 9, dividing both sides by 6, I get e to the power of 3x plus 1 is 9 over 6. You can simplify, but I'm not going to. What is 9 over 6? 1.5? I'm lost. Yeah, 1.5. Fine. Not just me that's sleepy. It's just warming up. Mostly because I didn't want to carry through the fraction, but you can. So now what? We can take any log base, but when possible, it simplifies things a little bit if we take the log of the same base, right? And so now, step 2 from here is take the log, or take any log of both sides. Right? But one of the things that I want you to keep in mind is that if you have log base b, so if you take log base e in this case, of e to the power of blank, 3x plus 1, then it just equals 3x plus 1, right? Because the log and the e, or log base e and e, are going to cancel, and we saw why. So can't remember the exact proof, but just accept it. It's fact today. So you can be strategic about your log, or if you just always want to use log base 10, totally fine, right? It's going to be a little bit more math, but so here, what I'm going to do is I will use the natural log, which is log base e, since I have an e here as my base. Right. So then I take the natural log of e to the 3x plus 1 is the natural log of 1.5. So you don't want to forget to take the log of both sides, right? That's the most common mistake that I see. You remember, okay, I need to take the log, otherwise I can't get at this exponent. That's fine. But then you forget to take the log of the right-hand side. But because of the equal sign, right, what you do to one side, you have to do to the other side. Otherwise, they're not equal anymore. Okay, so now from this rule, right, one of the things that we could do is we could rewrite this as 3x plus 1, bring it downstairs, right? Let's do that just to visualize it. 3x plus 1 times the log of e, or the natural log of e, sorry. But if you do the natural log of e on your calculator, it'll be 1. So that was our strategic move. And why we use the natural log, because then we just have 3x plus 1 is the natural log of 1.5. The natural log of 1.5 is just a number. It's not a nice number, but it's just a number. Or I'm assuming it's not a nice number. It never is. Who knows? So now I can just solve for x, right? Same as always, right? Subtract 1 from both sides. 3x is the natural log of 1.5 minus 1. So x is the natural log of 1.5 minus 1, all divided by 3. And log of 1.5 minus 1 divided by 3, I get x is approximately, now if you wanted to leave it in the exact form, this is it, you're done, right? That's totally fine. But usually, I don't know, we like to give approximations. Negative 0.19817829973. But if you left it in exact form, then you're good. I'm happy. Yeah. Or here. They're both correct. I do want to see the exact form before the approximation, right? And so either way, you have to go to here. And then you're allowed to go here if you prefer. Yes. As long as you do a squiggly equals, I'm not going to be that strict on the test, but then you should absolutely be doing the squiggly equals. And keep maybe 4 decimal places. 4? Depends on what these values are. 4 kind of captures the action here. If you have a bunch of zeros, you'd have to keep more, obviously. Right? But I feel like 4 captures the essence of the value. Okay. How about another one? Another one. Same rules apply, right? If we're trying to solve for this thing, we're trying to solve for t. Now, first thing I'm going to have to do is I'm going to have to isolate the exponent, right? Which is going to require a little bit more work this time, right? First, I need to subtract 6 from both sides, and then I need to divide both sides by 2, and then I can take the log, right? And so let's see here. I'll write it out here. 2 times 1/2 to the t plus 6 is equal to 10. We're going to isolate the exponent. So I get 2 times 1/2 to the t is 10 minus 6. One half to the t is 10 minus 6 divided by 2, or just 2. Okay. So now I'm going to take the log of both sides. And what do you want to do? Do you want to use a common log, the natural log, or do you want to use log base 1/2? I don't know, it's up to you. Let's use the common log just to mix things up, right? And see, so here, if we use log base 0.5, which we can do, then it would look the same as here, right? The log base 0.5 of 0.5 becomes 1, right? Just by these rules here, log base b of b is equal to 1, right? So that's a rule. And so we could use 0.5, but how about now we're going to take the log of both sides. Let's use, I never use the common log, so let's do that. The log of 1/2 to the t is the log of 2. What you do to one side, you have to do to the other side. we know by by log laws, I can bring that t downstairs. So then I have t times the log of 1/2 is the log of 2. So t is the log of 2 divided by the log of 1/2, which is just a number. The common log of 2 divided by log base 10 of 0.5 t is -1. Why is that? Sidetrack, but still, skills that we already know. Why is it -1? I have the log of 2 over the log of 2 to the -1, right? But the log laws say that I could rewrite this as -1 times the log of 2. So then this is the log of 2 over -1 times, let's see here, the log of 2. And the log of 2 over the log of 2 is 1. So then I have 1 over -1, which is -1. All right. So that's why it's -1. You can use your calculator. That's totally fair game, right? But you have all these exponent rules and log rules just to make sure that it makes sense. Right? Have to be super limber around the exponent rules and the log laws. Log laws. It's funner to say. Funner. What's another way that you could rewrite this? You could use the change of base formula. Let's do that on this side. All right. Change of base says that if I have log base 10 of 2 over the log base 10 of 1/2, then that's going to be log base 1/2 of 2. Right? So then this is equal to log base 1/2 of 2 by the change of base formula. Try log base 1/2 of 2, and you get the same thing, -1. Why? Exponent rules again, right? Because this, if we rewrite this as an exponent, right, 1/2 to the power of something equals 2, right? So here, we can rewrite as an exponent 1/2 to the power of something is equal to 2. This is 2 to the -1, right? If I rewrite 1/2, it's 2 to the -1. But if I just want it to be 2, then 2 to the, or 1/2 to the -1 is going to move it upstairs, right? And let's see how that works. 1/2 to the -1 is equal to 2. Right? By the exponent rules, I can rewrite 1/2 to the -1/2 as 1 to the -1 over 2 to the -1. I'm going to run out of space here, so I'll just, or maybe I'll, okay. One to the -1 is just 1, right? And so, or I can bring it downstairs, that's fine too. So let's do that. 2 to the -1 moves it upstairs. So then I have 2 to the power of 1 over 1 to the power of 1, which is 2. Right? And so you can confirm that it should be -1 many, many different ways. Okay. And so for that reason, right, I'm marking your work on this test and just your work, right? So you have to show every little thought that you had. Now, of course, this is all you have to show, right? But then there are lots of little ways that you can check your work, check your answer. And so that's fun, right? Huh? And what are we doing over here? Expanding our mind. We're building muscle, exponent muscle and log muscle. Huh? Feels good. We're going to be so good with exponents and logs. For some reason, a lot of people don't like exponents and logs, but I love them. They're so fun. They're so fun. Oh, I guess all you had to show is this. It was a little bit longer, actually. We did a little bit more. But once you've got them wrangled, then they're yours, right? You can move around these exponents and logs, and it's all fun from there. Let's see here. How about another example? Oops, that's not what I wanted. Word problems. Everyone's favorite. Not mine. Tuition's currently $1,050. That's cute. And is growing 7% each year. When will tuition exceed $2,000? So what are some things that we're drawing on? We're drawing on the general formula for exponents. So here, let's call it T of t. Why not? Tuition as a function of time. You can use f of x if you want, but sometimes I just like to get fancy. Is a times 1 plus r to the power of t. Hopefully, I feel like I'm missing something, but I don't think so. The starting amount is 1050. 1 plus 7% each year is the rate, so 0.07. And we want to know at what t does this tuition equal 2,000, right? It's only going to go up, right? It's growing 7% per year. So what we can do is, if it's going to exceed 2,000, we can just find the time point where it hits 2,000, and then anything after that is going to exceed 2,000, right? So usually, even though this should be an inequality, right, greater than 2,000, I don't like to deal with inequalities if I don't have to. So then I'm going to find the value where the tuition is 2,000, and then anything after that, I'll make a note here. We find the tuition, or the t, where tuition is equal to 2,000. Any t after that, t of t will be greater than 2,000, right? It'll exceed 2,000. Oh, and Forgot a key component, the t. So now, what can we do? Well, first thing, I can simplify 1.07, right? But I'll parking lot that for a little bit. I need to isolate the exponent, right? And so I need to divide both sides by 1050. So 2000 divided by 1050 is 1.07 to the power of t. Right. Isolate the exponent. Does that equal anything nice? I knew it. All right. I'm just going to leave it as is then. You don't want to start using any approximations here, right? You want to keep all your values. So even if you do use the decimal approximation, just make sure you keep all your values in your calculator and use them. Because what do we have to do next? To access the t, need to take the log of both sides. So now, I'll use my favorite log, the natural log. Do you have a favorite log? Log base 10. No! Thank you. Love me that natural log. Yeah, we're not engineers. Well, you guys are. I'm not. Well, 7 to the power of t. Any log will do. Right. What would be the sneaky, convenient, sort of convenient log to use here? Log base 1.07. Ugh. Right? Then the log laws say that log base 1.07 of 1.07 to the power of t is just t. But then you've made a total mess over here. So it's kind of a trade-off, I guess. Okay. What can we do next? This just stays as is, right? And so one of the things, instead of rewriting it, you can just leave it blank until you need it again, and then you can write it on the line where you need it, right? That way you don't have to rewrite everything if it stays the same. It also makes your work a lot cleaner to look at, right? If nothing's changing, then just don't bother writing it. So it'll look like this. T times the log of 1.07. Oh, I said it, didn't I? The natural log of 1.07. I'm trying not to. The natural log of 1.07 is just a number, so I can divide it over here, but I'm also going to use my switcheroo, my revolving door. What am I doing? I'm rewriting t times the natural log of 1.07 on the left-hand side and the natural log of 2000 divided by 1050 on the right-hand side. But then in the same move, I'm dividing the natural log of 1.07 over to the right-hand side. Rude. I know. Natural log of 2000 divided by 1050 divided by the natural log of 1.07. See, it's not so bad. I like to have what I'm solving for on the left-hand side, everything else on the right. This is the exact value, but we can find approximate value. 2000 divided by 1050 divided by the natural log of 1.07. T is approximately 9.523645992 years. Anything after 9.523645992 years, the tuition's greater than 2,000. What could you have done? What have we done? You could have used the change of base formula, right? And you could have said, well, this is actually equivalent to, right, by the change of base, this is the same as the log of 1.07 of 2,000 divided by 1,050, which is that sort of convenient value of log that we were kind of toying with initially, right? We said, well, I could be sneaky and I could use log base 1.07, and then I wouldn't have to deal with a log on one of the sides at least, right? But you get the same answer, right? And you can check it on your calculator. But I promise they'll be the same. Okay. Any questions about that? Okay. Where is it? Oh yeah, I made a note to myself, which is just a tiny arrow, which I thought would be easy to spot, but it wasn't. A more official guide, right? This is what we've been doing. So solving exponential equations, you're going to isolate the exponential expression. You can, or if needed, take the log of both sides. Notice it doesn't specify the base. And then utilize that property where we bring down the exponent. If you've got it inside a log, then you can rewrite it with the exponent outside, and then use algebra to solve for the variable. Just easy peasy. Use algebra. Well, yeah. There was another example in here, yes, that I thought would be kind of fun. So in chemistry, as you know, pH is a measure of the acidity or the basicity of a liquid. When I was reviewing this last night, I could not read this word. Basicity, or is it basicity? No, basicity, I think. I actually don't know. Of a liquid. The pH is related to the concentration of hydrogen ions, little H plus there, measured in moles per liter by the equation. pH is the negative common log, so log base 10 of H plus, whatever, hydrogen ions. Can you tell I don't know any chemistry? None, zero. I guess I took first year chemistry, but that was a long time ago. And then there's a per Lieber. I think there's another typo, but I can't remember where it is. But if a liquid has concentration 0.0001 moles per liter, determine the pH. So that's our part A. Determine the hydrogen ion concentration of a liquid with pH of 7. So that'll be our part B. So two things that we can do with this relatively simple equation. We've got pH, which, how about pH is just one thing, But what if I let pH just be key in our calculations? Because otherwise it looks like it's two variables, to me, at least. And you're welcome if you feel confident in your ability to always rate pH as one thing, that's totally fine. I am not confident in myself. So then P is the negative log of H plus so we had 0.0001 moles per liter, and that's my H plus. So I can replace this and I can say negative log of 0.0001. Couple of ways that you could do this, right? You could notice that this is log base 10, right? 10 to the power of something is 0.0001, right? And so that math is relatively fine. Or you can use your calculator, log base 10 of 0.0001. And I get making sure you keep that negative. Why? pH of -4 sounds terrible and unlikely. Did I do the right number of zeros, I wonder? 1, 2, 3, 4. Yes. Right. Let me just check. Of course, it's only giving me scientific notation. Sold? No, can't tell.
Oh, I'm still getting statistics up here. Can I put negative log in my function?
Yes. Just use the negative button and then do log base 10 of 0.0001 and you'll get 4. Yeah. It was just because I only did this, so then I have to keep the negative. But I'm also trying to emphasize that you have to keep the negative regardless. Otherwise, you get a weird answer. So then the pH would be 4. Okay. Determine the hydrogen ion concentration of a liquid with pH of 7. So now we know the pH and we want to try to solve for this hydrogen ion concentration. So now I've got P is negative log of H plus, and I've got a pH of 7 is the negative log of H plus. So I'm trying to solve for that H plus. I'm going to do what? First thing I'm going to do is I'm going to isolate the log, because how can I get rid of logs? I can raise it to the power of the base, right? As long as I do it to both sides. So then I can say -7, right? Just divide by -1 by both sides, but that just turns into a -7 is the log of this H plus, log base 10. So now, what can I do? I can take 10 to the -7 is 10 to the log of H plus. Remembering that this is log base 10. So then 10 to the power of log base 10 is going to drop out. And let's go back to where those rules are. B to the log base b, 10 to the power of log base 10 of x is just equal to x. So that's the rule that we're using, rule 2, I guess. So now 10 to the negative 7 is going to stay, but now I have 10 log base 10 is going to cancel, and I'm left with the h plus. So h plus is 10 to the negative 7. And I would just leave it at that.
So when you do your little negative switcheroo on the 7 there, it doesn't affect what's in the log bracket?
Here?
Here, yeah.
No, because the negative 1, so this is technically negative 1 times the log. And so I'm dividing by negative 1 here. But 7 divided by negative 1 is negative 7. So I just skipped that step.
Yeah, I was just wondering if it changed what was in the brackets of log to negative also.
So here, you could have reversed this, and you could have said, well, just as easily as I can bring the exponent out, I can shove it back in, and then I would have the log base 10 of 1 over h plus, if you wanted to. And then you wouldn't have a negative 7 here.
We have a negative in the brackets.
But then you would have 1 over h plus here, which is equal to 10, or sorry, 7. 10 to the power of 7. So you could do that. Should I write that down?
No. I was just making sure
Too late.
When you switch to negatives, it doesn't make what's in the bracket negative also.
No, because it's multiplying the log. Yeah. Nice. So, or you could have rewritten as the log of h plus to the negative 1. 1 over, which is the log of 1 over h plus. Oops. Okay. I want to get to multiplying, hey, and dividing. Let's see if I copied it. Nope. Exponents, but I did keep a question like this, or 2 questions like this on your assignment, I think, from 4.3. And you have the skills to get there, right? Moving from a continuous growth rate, which looks like a times e to the power of k times x. Thank you. What we can do is we can say, okay, if I have a periodic growth rate, right, this looks similar. What's happened? I've replaced 1 plus r with e to the power of k, right? And so here, this is what I wanted to grab. Let me try it again. So you can move between continuous growth rates, which look like this, and periodic growth rates, 7% per year, that kind of thing. Whereas 7% continuously would be the wording. So then if we look at compare and contrast, f of x is a times 1 plus r to the power of x versus f of x is a times e to the k times x, writing it nice and lofty so that we can see that these two things are equivalent, right? Oh, this is a bad x. So then you can convert between the two, right? As 1 plus r is equal to e to the k. So if you want the continuous growth rate k, then you have some r, right? So then 1 plus r is equal to e to the k, where k is the continuous growth rate. And r is the periodic growth rate. That doesn't spell periodic growth rate. So you might want to solve for r, given some continuous growth rate, e to the power of k, right? And then minus 1 gives you r. Or if you're trying to solve for k, you're going to need to involve some logs, probably a natural log, in order to bring down that k. Let's see here. Oh, it's wrong spot. Population grows 10% each year. Find the continuous growth rate. So we don't have a starting point. What could you do? You could just pick a general starting point, right? Maybe 100 or something that you like to work with. 1 might be nice, right? But they're just going to cancel anyways when you set these two equal to each other, because they're both functions f of x. And so eventually they'll cancel out and you'll be left with this. So what we have here is we have 1 plus r is e to the power of k. So we have r is 10% each year, so 0.1, and we want to solve for k. So we have 1 plus 0.1 is e to the power of k. So I get 1.1, 0, just make it look fancy, I guess, is e to the power of k. To get that k downstairs, well, first thing I have to do is isolate the exponent, which I've already done. It's already on its own, so that's good. And so now I'm going to take the natural log of both sides, 1.10 natural log of e to the k. K is brought downstairs, so then I have the natural log of 1.10 is k, oops, times the natural log of e. But the natural log of e, log base e of e is 1. So then this, of course, is equal to 1, which is why I chose the natural log. Otherwise, I might have log base 10 of e, right? And that's fine, but then you'd have to calculate that. Solving for k, well, I'm done. K times 1 is the natural log of 1.1. K is the natural log of 1.1, or k is approximately 0.095310179.8. but I would probably just leave it as the natural log of 1.10. In terms of interpretation, this is easier though, right? What does this say? Continuous growth rate of 9.531% per year is equivalent to 10% per year, right? In the periodic growth rate. Kind of weird, right? But the difference here is compounding continuously and compounding annually. So different rates. Get you to the same endpoint. Yes. Thought I said something weird. Incomplete, yes. Weird, no.
What's your answer for that?
This one? The 10 to the negative 7? Is that the one you mean?
7.
Yes.
Oh, okay. All right. Like a steel plane. Okay.
There.
Sorry.
Quite all right. Make a beautiful 10. It's a little almond shaped, my 0. Okay, good. Think we're ready. We're ready. So here they've got a nice summary, but what we want to talk about now is the sum of logs and the difference of logs, which is that log law on your formula sheet that you got today that we haven't talked about yet. So the rule says, or the law says, that if you have logs of the same base being added together, you can rewrite it and simplify it as the log of that base and then multiply the values inside, right? So multiplication inside, if you want to split them up, then it turns into addition of the logs. So here, multiplication inside the log turns into, can go the other way too, but turns into addition of the logs.
So you would just want to split them up, like going the other way if there was like one variable in there. Is that what you mean?
Usually we have 2 variables. If you want, now I'm blanking, what's an example that we're about to see here? Usually we use it to simplify something gross. Like if we have the natural log of 4.1 and the natural log of 10 being added together, then that's the same as the natural log of 4.1 times 10, right? And so then you just have to do it once. Where this came from, or where the value came from, was before calculators, right? If you have some nasty multiplication, then what you can do is you can rewrite it in terms of addition of logs, which is easy to do, right? Adding things is typically easier than multiplying things. And so that's where it came from, but it's also a nice rule to have. So usually we use this, usually used to simplify expressions. we're going to move back and forth. But in general, we're just going to use it to simplify things, right? Simplify our expressions. Remembering that this, you could rewrite a over c as a times c to the negative 1, right? And then everything else falls into place, right? This is the same as a times c to the negative 1. By the addition property, right, this becomes the log of a plus the log of c to the negative 1, which is the log of a plus negative 1, right, times the log of c, which is how we get the log of a minus the log of c from here. So you don't really need this property. You only need this property, and then you need all the other rules of exponents and logs, and then you can get here. Right? But you don't need this one. Well, we'll use it because it's stated, so why not? Right. But in life, as long as you remember this one, then you're safe. Let's see here. Rewrite the following as a combination of single log functions. There are lots of different approaches that you could take. You're going to end up in the same spot, so it doesn't matter. I'll give you some time to try it. What's one place to start? I could split up the division using subtraction. Let's start there. And like I said, there are lots of different places that you could start, and you'll end up in the same spot. The log of 5x squared over y to the 4th is the same as the log of 5x squared minus the log of y to the 4th. I can split the 5 times x squared, right? This is a times c, right? And so then I have the log of 5 plus the log of x squared minus the log of y to the 4th. Because I'm about to do the same move for both of these, I'll do them in one line. So this becomes the log of 5 plus 2 times the log of x minus 4 times the log of y. Nice. So as long as you got there, then you're good, right? What's another way you could have rewritten this initially? You could have rewritten this as 5x squared times y to the negative 4, right? And then you're multiplying three things, which you can just add each part together, but then you've got a negative 4 that you could bring out front, and you'd end up in the same spot. Right? Usually we want to write something the other way. Depends on what's easier to solve for, right? If this is easier to solve, for example, if you forgot your calculator or something like that, then imagine that. That'd be crazy. Then this would be easier to solve potentially than the big gross one. If we have to rewrite this as a single log, right, now you're gonna zip it back up. Right? You're essentially working in reverse, right? I would bring this 2 into the exponent and the 3 into the exponent, right? Let's start there. So then I have, I'll just rewrite it. 2 times the log of x plus 3 times the log of y is the same as the log of x to the power of 2 plus the log of y to the power of 3. That's allowed. Move back and forth. Now I have the same base and I'm adding logs of the same base, which means I can simplify this as the log of x squared times y to the power of 3. And then you're done.
That's plus,
In here, multiplying. Because, so the log is, it's not linear, so you can't distribute it. And so that's the problem. So if you have multiplication in here, then it turns into addition. But if you have addition in here, then you can't do anything. So it only works if you're multiplying or dividing. This zip up action. Okay. And it is on your formula sheet here. Log base b of x times y is the log base b of x plus log base b of y. And similarly, division turns into subtraction, right? And those are the only things that we can do, right? If I have addition or subtraction inside the log, then I'm stuck. There's nothing I can do. Well, there is something I can do. I can raise it to the power of the base to eliminate the base, right? So there are ways around it, but in terms of simplifying or expanding, there's nothing you can do. What if you have to solve log of x plus 5 minus the log of x is equal to 2? I'll give you a moment to give it a whirl. But what's the first thing you're going to have to do? Combine these into one log is my go-to move. Could put it all in the exponent, but it'll get messy. Oops. So if I have subtraction of logs of the same base, then I can rewrite that as the log of x plus 5 divided by x is equal to 2. I want to get at what's inside that log, right? What can I do? I can raise everything to the power of 10, both sides, right? This is log base 10, presumably. And so I can do 10 to the power of log base 10, which I don't write, of x plus 5 over x is equal to 10 to the power of 2. You don't want to forget this, because if you forget it, it makes a real mess. You have to do it to both sides. But now, this cancels. That was the point of raising everything to the power of 10. So now what I'm left with here is x plus 5 over x is equal to 10 to the power of 2. I don't need those brackets anymore, but I'm just using them to emphasize that they're just one thing that drops down. Yeah. Now we know how to solve for this. We know how to solve for x here, right? We have x plus 5 is equal to 10 squared times x. Guess I could write that as 100. 100x, right? Multiplying the x over here. And then collecting like terms of x's. I'm going to have 5 is 100x minus x. So 5 is 99x. So x is 5 over 99. Which is nothing nice, but let's try it. The log, so here we can always check it. The log of 5 over 99 plus 5, minus the log of 5 over 99. Does it equal 2? Let's try it. 5 over 99. I'm going to store that somewhere in A. Now, log base 10 of A plus 5 minus log base 10 of A. It is 2. Whee! Oops. So you can always check your work. One thing, let's see here. Okay, I'll hold off. Fine, I'll hold off till next day. I do want to, so we didn't quite finish 4.4. I do want to wrap it up on Friday, but I also remember that you don't have a lab on Friday, so it's okay if you don't want to make the drive here. You can join on Zoom, or you can get caught up later, or I don't know, sleep in, I don't know. But I'll just finish 4.4, and then that'll be the cutoff for the test, which we're keeping on Monday.
What else
Feels
do you have
good.
on Monday? Do you have anything else? Breakfast?
Chemistry.
No, but I mean like assignments or labs. Anything you do Monday?
So you'll be fit for fight. No, I haven't. So I'll do that. But I haven't made it yet. It's the problem. I'm gonna stop this recording.